talked about the error correction procedure in classical computations and considered the 3-bit code. In this lesson, we discussed the quantum error correction. But before that, we will point out the main features which one faces when dealing with quantum physical systems like qubits. Firstly, the quantum evolution of a qubit or a system of qubits is a continuous physical process. A simple illustration could be given in terms of the single-bit operations we considered before. We recall that such operations can be represented by rotations on the Bloch sphere. For example, the x operation, that is the quantum analog of naught, is represented by the psi state vector's rotation about the x-axis by an angle of p. In the real physical system, the logical operations are usually performed with a certain finite precision. It means that the rotation angles become a little bit distorted. The rotation angle for the x operation is now not just p, but p plus small addition, caused by different inaccuracies during the operation. This will lead to an error. Despite the addition is small, but it could be absolutely random over a certain range, and thus the number of errors in general will be infinite. Instead of a point on the Bloch sphere, the situation corresponds now to a certain area around this point, and there is an infinitely large number of quantum states in such area. We have already discussed it before. At first, it seems like an error correction procedure should be chosen uniquely for each error, that is, uniquely for each state. Secondly, as one measures the qubit being in a superposition of basis quantum states, the quantum reduction happens and the superposition turns into one of the basis states. It means that in order to use the qubit for further computations, one shouldn't perform the direct measurements of the qubit to define its state. Thus, the error syndrome should be defined without direct measurement of the qubit. Thirdly, according to the no-cloning theorem, it is impossible to create an identical copy of a qubit in an arbitrary quantum state. As a result, one cannot create qubit copies in order to find out whether there was an error in the channel or not. Despite all differences between quantum and classical theories, they have a lot in common. Actually, the whole approach is aimed to solve the same problems, to model the errors occurring in the channel, to perform an error-resistant information encoding, and to create the error correction procedure. Let's now discuss the models of quantum errors in detail. As we did in the classical theory, we consider independent single-qubit errors and multi-qubit errors. Despite the correction of multi-bit errors is, of course, more complicated, these approaches are quite similar. That's why we discuss the correction of single-bit qubits independent errors only. Such errors are usually being considered as a result of the interaction with the environment, which is a big quantum system to which all other physical objects except the qubit we consider belong to. Besides, it allows one to describe the uncontrollable logical operations we discussed before. Since the environment interacts with the qubit and defines its evolution, it is referred to as quantum information channel, by analogy with the classical one. So, let's find out what is happening with the qubit due to its interaction with the quantum information channel. Let the qubit be in a pure state psi at the initial moment of time and the channel be in the pure state E. Then the qubit plus channel quantum system state is described by the tangent product of psi times E. Since we consider, in fact, the qubit and the rest of the world, their interaction will lead to a unitary transform on the whole system's state, which becomes entangled. At first, consider the case of a qubit being prepared in the basis state 0. So, psi equals 0. And thus, as a result of interaction with the channel, the system state is described by the superposition 0, by the following superposition. E1 plus beta 2, 1, E2. We denote this expression as 1. So, after the interaction with the channel, the qubit will have the probability of beta 1, the magnitude of beta 1 to the second degree remain unchanged, and the probability of beta 2 squared to perform flip. Similarly, we have the following superposition describing the qubit that was prepared in the basis state 1, so when the psi was equal to 1. The interaction do this thing. B3, 1, E3 plus B4, 0, E4. We denote this by 2. Now, if we combine these two results of 1 and 2, we can see that in general case, the total state of a system of a qubit in the superposition state psi, which is now alpha 0, 0 plus alpha 1, 1 interacting with a quantum channel in a state E, can be written as alpha 0, 0 plus alpha 1, 1 E turns into the following superposition. It will be a little bit tough, but it's okay. 0 E1 plus alpha 0 beta 2 1 E2 plus alpha 1 beta 3 1 E3 plus alpha 1 beta 4 0 E4. Okay, let's now combine the terms in the following way. We'll move to the next slide and write it down here. So, we'll have 1/2 alpha 0, 0 plus alpha 1, 1 multiplied by beta 1, E1 plus beta 3, E3 plus 1/2 alpha 0, 0 minus alpha 1, 1 multiplied by beta 1, E1 minus beta 3, E3. This is not the end. Plus 1/2 alpha 0, 1 plus alpha 1, 0 multiplied by beta 2, E2 plus beta 4, E4. And it is still not the end. Plus 1/2 alpha 0, 1 minus alpha 1, 0 multiplied by beta 2, E2 minus beta 4, E4. Okay, that's all. After that, it's convenient to use the definitions of single qubit operations which were introduced earlier and rewrite the qubit state after the interaction. So, what we've got here? What is it? It is actually the state psi. And what is it? This is actually the state Z-psi. Remember the previous lessons. What is it? This is actually the state X-psi. And the most brilliant students will understand that this is the XZ-psi. So now, the result of interaction between the qubit and the channel turned out to be the superposition of 4 discrete transforms. I will write it in the full way, but we have here 1/2 on the state psi and some state of the channel plus 1/2 Z-psi and again some state of the channel plus state 1/2 X-psi and some state of the channel plus the state 1/2 XZ-psi. And again, something connected with the channel. Each transform in the superposition, except the identity one, which is represented by a first term, corresponds to a certain type of errors that may occur in the channel. So the second term corresponds to the corresponding to the Z transform leads to a phase error. We can see it here. The third term corresponding to the X transform leads to a bit flip error. We can see it in the value of bits. And the fourth term corresponding to the XZ transform will lead us to both bit flip and phase errors at once. You can see it just the bits are flipped and the sign is opposite. So, the interaction between the qubit and the channel can be represented by a sum of 4 discrete transformations, as you can see on the slide. Each of these transformations, except the identity one presented by the first term, corresponds to a certain type of error that may occur during the qubit-channel interaction. So, the second term describes a phase error, which is the election of the Z logical element on the qubit state. It leads to the sign inversion as it's on the slide. The third term corresponds to a bit flip error, which is the action of the X logical element on the qubit state, psi. It leads to a bit inversion. The 0 state is replaced by the state 1, and the state 1 is replaced by the state 0. And finally, the fourth term leads to a qubit and phase errors at once for the action of X and Z logical elements. It means both sign and state inversion. Of course, these 4 errors don't appear in a channel together always. As it was in the classical case, it depends on a channel's quality. In particular, the error probabilities in the channel could be so small that they can be neglected. And the channel can be considered as an error-free channel with good precision. Despite the continuous nature of the qubit plus channel system interaction, we should only learn how to correct these 3 error types instead of an infinite number of them. Moreover, we've learned before that these errors can be represented by the Pauli matrices. And as any function of Pauli matrices or a product of them can be rewritten using the Pauli matrices and identity matrix, any combination of sequence of these errors will reduce to these 3 error types. So, after we've got the error models, let's now turn to the information encoding. The encoding is based on the redundancy principle as it was in the classical case. It means that the encoding should proceed in such a way that if an error occurs and a part of information is lost, the rest part of information should be enough to restore the initial information. As it was before, the encoding procedure had the following form. At first, a set of auxiliary bits in the states 0 are added to the initial qubit in the state psi. Then a certain encoding unitary transform on the whole system is performed. The psi qubit turns into the qubit psi enc. The scheme of such an encoding for the 3-bit code is depicted on the slide. Only the bit flip errors which swap 0 and 1 states are considered. We will discuss this scheme in the next lesson. The fact of interest for us here is that the pure quantum state Psi turns into the entangled state of 3 qubits during the encoding. It means that since the no-cloning theorem for bits was to create a copy of the qubit, we realize the redundancy principle using the quantum entanglement and proceed the further decoding. The quantum entanglement is being used in all of the quantum encoding schemes. And now let's discuss briefly the features of the quantum information decoding. Firstly, as it was before, not all of the errors are correctable. It means that the encoding and error correction procedures do not protect us from all of the existing error types. That's why the quantum information channel should be developed with high accuracy. Secondly, the correctable errors must be distinguishable, and so the information encoding should be proceeded in such a way that allows one to distinguish 2 different code words from each other if an error has occurred. It means that we have several operations and each of them corresponds to a certain error type that may occur in the channel. As any of these operations act on a pair of different code words, which now is an entangled quantum state, we have to obtain 2 distinguishable, that is, orthogonal quantum state. The general quantum error correction scheme is presented on the last slide. The qubit in the state Psi and the pair of ancilla qubit in 0 states are brought to the input. Then the encoding procedure, that is a certain unitary transform U-enc, is applied. After that, an error may occur in the encoded qubit that corresponds to an error operator EQ, acting on the logical qubit state. Finally, if the error is correctable, the detecting procedure is applied. It corresponds to an action of the R transform. As a result, we restore the initial qubit state Psi and transform the affection of the error to the states of ancilla qubits. In some cases, one could reverse the action of an error operator and restore the code word, which is the entangled state of an initial and ancilla qubits. This would be interesting since the encoding-decoding operators can also go with errors. And the total number of errors during the computations should be minimized. In our next lesson, we consider all the topics of this lesson applied to the 3-qubit code. Thank you for your attention.